Hey guys, these are your refraction notes. Alright, we're going to start off with a definition of index of refraction. Refraction is basically just the bending of light. Alright, refract is the same thing as bend. Alright, so the index of refraction, okay, it tells you it's a value which indicates the optical density of a substance. What happens when light enters a new substance, like glass, is it slows it down because glass is much denser than air. Glass has a very high index of refraction. Its index is, as an example, it's 1.49, while air, I'm going to put that near the bottom here, has an index of refraction of 1. Now, when light enters glass, it's more dense, has a higher index of refraction, 1.49, so it slows down a little bit, and that causes it to bend. Alright, so we'll give you some more examples of index of refraction. I'm going to move glass just down a little bit on the list into the middle here. Glass is 1.49, and some other index of refractions are diamond, very dense, 2.42 is an example. You've also got something like diamond, but not quite. Cubic zirconium. It's a rock which is used to imitate diamonds. It's a fake diamond. And then you got water, somewhere between glass and air, about 1.31. And each substance has their own index of refraction because all different substances have different densities. So write all those down, and the importance is that a physicist can calculate these index of refractions. We'll do that later. But when they calculate it, they could see whether a diamond is a real diamond if they get 2.42. But if they calculate closer to 2.15, they could know it's fake. So that's how you could tell if you have a fake diamond or not, using the index of refraction. One thing I should indicate, N, write that down next to index of refraction. That's the variable we use to indicate index of refraction. So for diamond, it's like N equals 2.42. Alright, air, N equals 1. Alright, that's what we use. It just means number for index of refraction, N. Okay, so how does light bend when it goes from one index of refraction to another? Well, light can go from a low to a high index of refraction, or from a high to a low index of refraction. So let's do those two cases here. When light goes from one substance to another, so say we'll do low to high, so we'll do air to water as an example. 1 to 1.33, right? How does it bend? Low to high. You saw this in the investigation. If draw light coming towards the interface, so we call that right there, between air and water, and then that light bends towards or away from this normal line here. Well, we saw that when it goes to a higher index of refraction, it bends towards the normal line, like that. And when light goes from a higher index of refraction to a low, it bends differently. Again, the solid line, call that the interface. It's the division between one substance and another. So let's choose another. Let's choose cubic zirconium. Why not? So cubic zirconium has a 2.15, and say that goes into water, 1.33. How is that light going to bend as it goes from a high to a low index of refraction? Well, we saw that when that happens, it goes away from the normal line instead. So low to a high index, it goes towards the normal line. From high to low, it bends away from the normal line. Alright? So how does this affect what we see on a daily basis? You know, when I look through glass, I know light bends when it enters the glass. That happens. We saw it in the investigation. But why do we still see things normally through a glass door or a window? So draw this diagram below where I drew a glass door, alright, in the middle there. There's air on one side of the door and air on the other. And I'd like you to label the index of refraction of each of these. So air is n equals 1 on each side, and the glass door is n equals 1.49 in the middle. So let's think about when light enters the glass door, how does it bend? It goes from a low index to a high index. So that means it bends how? Think about it. It goes towards the normal line, right? This normal line right here is what it goes towards. So it's bending in and towards the normal line. And then when it exits the air, exits the glass door back into the air, it goes from 1.49 to a lower index now of just 1. So in that case, when the index lowers, it bends back away from the normal line. But see that when it bends back away, it begins to go in the direction it was heading in the first place when it was in the air. So if this is the air coming, light coming from outside to inside, and this is a window, it bends in and then bends back out to where it was going in the first place. So the glass, because it has to enter and exit the glass, really doesn't affect what we see. Yes, light bends in it, but it bends back again. Okay, so the last thing I'd like to look at is this idea that refraction can cause us to see weird phenomena. Alright, so you did a demonstration where there was a dot on the bottom of the cup and you couldn't see the dot. Then when you poured water in, all of a sudden you could see the dot because of the way that the light bent when it exited the water. Alright, so this problem is very similar to that. It's called the fish hunter. Alright, so say there's a fish in a lake and you're hunting it with a spear. Now, the question is, should you aim the spear directly at that fish right there? Or will that cause you to miss it? Because when you're looking at the fish, the light bends when it comes out of the water into your eye. So where does he see the fish, and where should he aim it to actually hit the fish, aim his spear? Alright, so first thing I want you to do is draw a diagram and then label water's index of refraction, 1.33. The fish is in the water, right? And air has an index of refraction of 1, right? So now, in order to see the fish, light is going to exit the water and it's going to bend into his eye. So light from the fish comes out of the water, draw it towards that normal line right there, in a straight line. And then when it exits the water, it goes from a high to a low index of refraction. So how does it bend when it exits the water if it goes from a high to a low index of refraction? Into the air is lower index of refraction, so it bends away from the normal line and straight into his eye. So this light from the fish down here, it actually bends to the right a little bit for him to see it because it's going from water into air. But his eye is pretty stupid, and his brain always thinks that light travels in a straight line, just like when we talked about mirrors. Our brain always believes that light doesn't reflect or refract, that it bends, that it doesn't bend, that it travels straight, So our mind actually traces that ray we see back to boop, right there. See that dotted line? That's what our mind believes the light is coming from, because it thinks light goes in a straight line. It didn't think light came from down here. It doesn't know that light bends. And we would actually see the fish right there. So number one, where does he see the fish? Higher or lower? Well, our mind traces it back in a straight line to a position that is higher than where the fish is actually located. And where should he aim his spear? Higher or lower than where he sees the fish? So the question is, if he wants to hit the fish, he sees it right there because the refracted ray is traced back straight. But where should he aim now? So he sees it here, but he should aim his spear a little bit to where the fish actually is. That's where it actually is. He should aim it right down there in purple. So he should aim it a little lower because his mind traces it back higher than it actually is. So actually, spear fishermen, even before they knew any physics at all, knew this concept that if you see a fish high in the water, that the light bent into your eye, and it bent away from the normal line. So you actually think it's higher when it's lower, and they would always aim lower than where they actually see it.